NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
Envision a gigantic troupe played by a ceaseless number of stars, planets, and moons, all performing together grandly. Anyway, there is one explicit piece of this troupe that has confused cosmologists for a huge time frame. Exoplanets. These are conventional planets that exist outside our nearby planet group, stowed away somewhere deep in the Milky Way. You may be shocked to find that, among the tremendous number of enormous objects, there are exoplanets so like Earth, so tantalizingly similar yet confounding, that they may be our planet's sublime twin. We plunge into the spellbinding realm of Proxima b, found simply 4.2 light-years away. The James Webb Space Telescope is revolutionizing our quest to comprehend these divine mysteries. Envision a moment when your mind ventures across the vast scope of our universe. The Milky Way, home to more than a quadrillion exoplanets. That's a number with 15 zeros. To put this into perspective, if each of these exoplanets were the size of a grain of sand, we wouldn't fill the Grand Canyon. We'd have enough to create a new landmark on Earth. A Grand Canyon 2.0, stretching an incredible distance. Even more surprising is that around 20% of these heavenly bodies are deemed Earth-like in terms of geology and atmospheric structure. This implies there's a 1 in 5 chance of finding a twin of our planet. Yet the story doesn't end there. Alongside these planets, there could be another quadrillion moons, rocky satellites like our own moon, locked in a gravitational dance with their parent planets. If you've ever wondered about finding another celestial body capable of harboring life, the universe offers a surge of opportunities. Now that we've set the stage for a grand spectacle, it's time to introduce the master artist ready to paint its intricate details, the James Webb Space Telescope. This heavenly Sherlock Holmes, with its massive primary mirror and adjustable optics, surpasses even the most advanced optical instruments. Its 6.5-meter mirror is 2.7 times larger than Hubble's. Imagine the precision. It can detect even the faintest glow of a star billions of light-years away and then analyze the details of surrounding planets. What makes the James Webb Telescope revolutionary isn't just its observational power but also its state-of-the-art technology, including advanced sensors and spectrographs. These tools do much more than observe. They analyze and filter the unique light signatures emitted or reflected by celestial objects to determine their chemical composition, density, and even mass. Acting as a cosmic scientist, it can detect the presence of water, organic compounds, or even oxygen on a planet. The James Webb Space Telescope elevates our abilities from simple observation to scientific genius. It's not just an improvement over Hubble. It's a quantum leap. If Hubble's discoveries amazed you, prepare for an era of unparalleled revelations. As we expand our gaze across the intricate tapestry of the universe, it's worth focusing on one specific star in the celestial symphony, Proxima b. Since its discovery in 2016, this enigmatic planet has stood out as a Shakespearean character, filled with complexity and intrigue, captivating astronomers and anthropologists alike. Why does this matter? First, Proxima b is practically in our cosmic neighborhood, 4.2 light-years from Earth. To put this into context, if you could break the universal speed limit and travel at the speed of light, you'd arrive in just 4 years. About the same amount of time it takes for your favorite show to cycle through reruns. But let's dive deeper into why this proximity is so significant. We're talking about a universe that spans more than 93 billion light-years across. Finding a planet so close and so promising for scientific study is like finding a pearl in a mountain-sized pile, a gem that could hold secrets about life itself. In the grand tapestry of the universe, Proxima b is a vibrant thread offering profound clues that could redefine how we understand habitability and life beyond Earth. What excites scientists isn't just Proxima b's closeness to Earth, but also the tantalizing evidence that this planet isn't just Earth-like, but potentially Earth 2.0. Proxima b effortlessly resides in the habitable zone of its parent star, where conditions are neither too warm nor too cold, but just right for liquid water to exist. Imagine waterfalls, winding streams, massive lakes, and perhaps oceans as deep and mysterious as the Mariana Trench. Yet, before we start fantasizing about vacations on Proxima b, let's consider a few of its unique features. For starters, a single day on this fascinating exoplanet lasts a staggering 11 Earth days. Imagine sunrises that usher in a new day slowly, resisting the advance of noon, and sunsets that linger, creating mythical golden hours that photographers dream of. While this sounds enchanting, it also has significant implications for its environment and habitability. How would human biological rhythms adapt to such prolonged cycles of light and dark? Would we eat 3 or 4 times as much in a single day? Would we sleep differently? Life, as we know it, would be both tantalizingly familiar and frustratingly unpredictable. Perhaps nature is giving us a riddle wrapped in a mystery, challenging our understanding of what makes a planet habitable. You might wonder how we can gather accurate and reliable data about a world we've never visited. The James Webb Space Telescope wields its capabilities like a giant Swiss Army knife. It's more than just a telescope, it's a sophisticated research lab in the vacuum of space. Thanks to its innovative technology, astronomers don't simply observe planets, they analyze them through a prism of advanced scientific instruments. These instruments, such as spectrographs, examine the light emitted and reflected by distant worlds. Each element or compound in a planet's atmosphere absorbs or emits light at specific frequencies. By studying these patterns, scientists can perform a remote biopsy of celestial bodies, determining atmospheric pressure, density, and the possible presence of life-supporting compounds like water, organic carbon molecules, and even oxygen. This isn't just astronomy, it's space forensics. We don't passively wait for clues to come to us. We actively search for them, dissecting the atoms and molecules that form these complex worlds. The James Webb Space Telescope is not merely an eye in the sky. It's a highly specialized scientific marvel. As we refine our methods and probe deeper into the universe, the James Webb Space Telescope continues to unlock secrets from Proxima b and beyond. The data it gathers has the potential to reshape our understanding of habitability, atmospheric composition, and the conditions that foster life. Let's return to Proxima b, a planet that holds extraordinary promise. One of the most fascinating aspects of this exoplanet is its location around its parent star, Proxima Centauri, a red dwarf. Unlike our Sun, red dwarfs are smaller, cooler, and dimmer, making their habitable zones much closer to the star. This proximity raises critical questions about Proxima b's environment. The planet is likely tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This creates extreme temperature differences between the two hemispheres. However, if there is an atmosphere thick enough to distribute heat, the planet's twilight zone, the region between the light and dark sides, might be temperate and capable of supporting life. Yet, Proxima Centauri isn't without its challenges. Red dwarfs are notorious for their stellar flares, which can produce bursts of radiation strong enough to strip a planet's atmosphere over time. But scientists believe that Proxima b might have a strong magnetic field or other protective mechanisms to shield it from these effects. This is one of the critical questions the James Webb Space Telescope aims to address. In addition to studying atmospheric conditions, researchers are also on the hunt for biosignatures, signs of life. The presence of gases like methane, oxygen, or ozone in specific ratios could indicate biological activity. Spectral analysis of Proxima b's atmosphere will provide vital insights, offering us the chance to answer the age-old question: are we alone in the universe? The journey doesn't stop with Proxima b. The James Webb Space Telescope is a gateway to exploring countless other exoplanets scattered across the galaxy. From super-Earths with vast oceans to gas giants with moon systems that could harbor life. The telescope is redefining the boundaries of human curiosity and capability. As we gather more data, humanity stands on the cusp of a new era in space exploration. Proxima b is just the beginning, a stepping stone in our quest to understand the universe and our place within it. Imagine a future where we don't just identify planets as distant objects but as worlds with weather systems, ecosystems, and perhaps even civilizations. The implications for science, philosophy, and humanity as a whole are profound. The discoveries made by the James Webb Space Telescope are not just about distant planets. They are reflections of our own drive to explore, to question, and to seek understanding. Each discovery brings us closer to answering some of the most profound questions. How rare is life? What conditions are essential for it to thrive? And most importantly, what does it mean to be a part of this vast, interconnected universe? All in all, the James Webb Space Telescope grants us the tools to explore, discover, and redefine our understanding of existence. The universe is no longer an abstract concept of unreachable stars and planets. It is a living, breathing tapestry that invites us to unravel its secrets. Change our speculations and hypotheses about outsider universes into procedures to check or discredit them, upsetting our cognizance of what could exist past our blue dot. Right when you assumed you had uncovered the most dazzling layers of this cosmic onion, the story veers off in a strange direction, similar to a sci-fi thrill ride. Specialists using the James Webb Space Telescope found something exceptional from Proxima b, a transmission so unprecedented that it spread through scholastic hallways and virtual entertainment, named a potential technosignature. It was an electromagnetic emanation so many-sided and purposely planned that it indicated the presence of a high-level civilization. The aggregate heartbeat of mankind appeared to stop at the pinnacle of a disclosure that vowed to reshape our point of view on reality. Could this trans be the conclusive proof that we are not alone in the universe? Yet, as fast as it seemed, the transmission disappeared, abandoning a significant quietness and a labyrinth of unanswered inquiries. Was it simply a transient heavenly peculiarity, an enormous happenstance, or something more conscious, a coded message or an indication of extraterrestrial insight? This lone transmission cast a sad remnant of mystery over Proxima b, lighting extraordinary conversations and hypotheses. Was it a temporary irregularity, or part of a far bigger, more perplexing story than we can imagine? The incomplete, enormous story yet stands. Wait. The tale of our enormous investigation is a long way from complete. The ink has not yet dried, and new parts are still being written. This time, it's not just experts but also Harvard researchers driving a change in perspective as we continue looking for extraterrestrial life. They are not happy with only analyzing the transmission or peculiarities we've noticed so far. Rather, they are upping the ante by changing the James Webb Space Telescope into a sort of monster night vision telescope. They mean to look for artificial light sources in both the dull and enlightened districts of far-off universes. Really, ponder the staggering chance of identifying natural proportionality of cities, gleaming in the dark like brilliant flashes of civilization. Picture the shining light emissions from a city murmuring with cutting-edge life, emanating its splendor into the huge, grandiose seas. As we keep unwinding the secret of the universe, the journey for extraterrestrial life takes on new aspects. Beyond Proxima b, our excellent hunt digs further into the immense, unfamiliar locales of space. This pursuit is driven by mechanical progressions and a significant interest in our position in the universe. The quest for life beyond Earth, persistent leap forwards in cosmology, and space investigation have led to the discovery of various exoplanets with potential livability. Instruments like the James Webb Space Telescope, biomarkers, and ground-based observatories have enhanced our capacity to recognize and concentrate on these far-off universes. One especially enthralling area of examination is the quest for biomarkers, indications of something going on under the surface. These may include air gases, for example methane or carbon dioxide, which under the right circumstances could indicate organic cycles. The JWST's advanced capabilities go beyond basic identification. Its complex instruments can analyze the air composition of exoplanets with remarkable accuracy. By concentrating on starlight sifted through an exoplanet's atmosphere, researchers can identify chemical markers characteristic of life. For example, the presence of water vapor alongside key atoms like oxygen or ozone could suggest life-supporting conditions. One more road of examination involves concentrating on the conditions of these far-off universes. Environment models, in view of information from the JWST, assist with predicting whether an exoplanet's condition could support liquid water, a basic element for life as we know it. Researchers are especially inspired by planets situated in the habitable zones of their parent stars, where temperatures could permit stable liquid water. The pursuit additionally stretches out to the moons of exoplanets. A portion of these moons, particularly those within the livable zones of their host planets, could hold conditions suitable for life. For instance, icy moons in our nearby planet group, such as Europa and Enceladus, are believed to contain subsurface seas beneath their frozen hulls. Similarly, moons orbiting exoplanets could present equivalent circumstances where life could exist. Technosignatures and advanced civilizations. The idea of technosignatures has also gained speed. These are indications of cutting-edge civilizations that may be discernible through artificial designs or advances. This could include uberstructures like Dyson spheres, speculative developments intended to harness a star's energy, or regular patterns in radio transmissions. As we refine global collaborations and observational methods, the quest for technosignatures could uncover the presence of extraterrestrial intelligence. Global participation and public commitment to technical advancements. Global collaboration plays a critical role in the search for extraterrestrial life. Joint efforts among space agencies, research organizations, and private companies improve our capacity to explore space. For example, missions to Mars and other celestial bodies involve contributions from numerous countries, pooling resources and expertise to achieve shared goals. Public engagement and education are also essential. The excitement surrounding space exploration inspires the up-and-coming generation of scientists and specialists. Effort programs and educational drives cultivate interest in STEM fields and encourage youngsters to pursue careers in space science. Future exploration. The advancement of new technologies further adds to how we might interpret the universe. Advances in telescope design, data processing, and computational modeling work to enhance our ability to detect and analyze distant exoplanets. For instance, cutting-edge space telescopes such as the planned Extremely Large Telescope (ELT) and the Habitable Exoplanet Observatory (HABEX) promise much more detailed observations and deeper insights into the potential habitability of exoplanets. As we push the boundaries of our knowledge, each new discovery raises new questions and avenues for investigation. The search for extraterrestrial life is not only about finding alien civilizations, it is also about understanding the origins and potential diversity of life in the universe. It challenges our understanding and expands our knowledge of existence. The study of exoplanets and the search for extraterrestrial life are dynamic and evolving fields. With each advancement, we edge closer to answering some of humanity's most profound questions. As we continue to explore the universe, the possibilities for finding new forms of life and understanding our place in the cosmos remain limitless. The journey to find extraterrestrial life has already begun to redefine how humankind sees its role in the universe. That we might not be alone challenges the anthropocentric view of the universe and invites us to consider our planet as one of innumerable interconnected pieces in a vast and dynamic cosmic mosaic. If life exists elsewhere, even in microbial or primitive forms, it would significantly affect fields ranging from science and biology to philosophy and ethics. Such a discovery would provide insight into the comprehensiveness of life's building blocks and the conditions required for life to emerge. More critically, the potential presence of advanced civilizations raises questions about their technological and social development. How could they overcome the challenges of survival and resource management? Might they have insights into sustainability, energy, or conflict resolution that humanity could learn from? The role of citizen science and public participation. As the search for extraterrestrial life becomes increasingly accessible, citizen scientists are playing a crucial role in expanding the scope of research. With platforms like SETI at home, individuals can contribute computing power to analyze data for unusual transmissions. Freely accessible datasets from missions like Kepler and TESS also empower amateur astronomers to search for exoplanets or other anomalies. Engaging the public in these endeavors not only democratizes science but also fosters a global sense of curiosity and wonder. Education initiatives, sci-fi media, and open-access research are inspiring a new generation of thinkers and visionaries to participate in humanity's cosmic journey. Exploring beyond habitability. While much of the focus has been on finding Earth-like conditions, scientists are also expanding the scope to include conditions vastly different from our own. Life as we know it depends on water and carbon-based chemistry. But what if alien life forms use entirely different biochemistries? For instance, life could exist in conditions with liquid methane or ammonia instead of water. Some researchers are even exploring the possibility of silicon-based organisms or creatures that thrive in extreme environments, such as the crushing pressures of gas giants or the intense radiation around neutron stars. These considerations remind us that our understanding of life is limited by our own earthly experiences. To truly grasp the possibilities of extraterrestrial life, we must remain open to the idea that alien biology might challenge everything we think we know about life itself. Looking ahead, interstellar exploration. The next frontier in the search for life lies in interstellar exploration. While current missions focus on our solar system and nearby exoplanets, future technologies may enable us to reach distant stars. Concepts like light sails, nuclear propulsion, and even warp drives are being explored as potential means of achieving interstellar travel. One particularly ambitious project is Breakthrough Starshot, which aims to send small laser-powered spacecraft to the Alpha Centauri system. These probes could travel at a fraction of the speed of light, potentially redefining our understanding of the cosmos.